Okay, hopefully this is working. Okay, so let's start it. We have a lot of holidays in between, so hopefully everyone still remember the stuff we talked about. Any question from last time? This time we finished talking about those. Yeah, this time we cover a lot. We finished talking about the I guess introducing the delta functions and unit step functions, and then we start talking about system. And we once again we say systems are something that change a signal to another signal. So it's this arrow here that change the input signal X to the output signal Y. And there are continuous time system and there are discrete time system. And then we see this example of system again, physical example of system again, like RC circuit. And we see more mathematical formula of the system. So this is how we express system in terms of mathematical formula. We'll just we usually assume the input signal is X and the output signal is Y. Then we just give you some relationship between X and Y. And hopefully you can solve Y from those kind of relationship. Okay. And more example of automobile, and then this is some notation that will I guess we'll sometimes use. This block representation that lets you string together a whole bunch of systems in different way. You can do this sequential or serial or parallel, and you can have very complicated interconnect system, and even you have feedback loop. Later in the course, we'll teach you how to solve a system like this, like what's the stable result, stable state of this kind of thing. Okay. So that's a very quick review from last time. If not question, then we'll go to the harder part of the chapter, that are the system properties. So yeah, there are a lot of systems, and there are many properties that we think that worth us to label. Okay. And well, many of them. So I guess let's just go through them one by one, and also. Not quite spoiler, but those are important, at least in this class, as you will see a lot of them in the homework, and you will see a lot of them in your midterm or even final. So it will give you a system and ask you, do they have one of those properties, etc. Okay, so the first property is memory. So basically, the system remember things in the past or even in the future. Okay, so I think this is very straightforward. A system without memory means that it just it just react to what the input it is at the current time. So if the system is memoryless, means that this y of t is independent of anything other than x of t. So y of t only depends on x of t. So it just it just give you some input, and it will respond with the output immediately, and it doesn't remember anything in the past, and doesn't look at things in the future. Okay, so should be very intuitive. And otherwise, so the other way around, then it has memory. And similarly in discrete time case, then time goes from t to n. Okay. Okay. Question with the definition. Well, let's go to this. Okay, so here's an example. So we can have a very complicated system. So y of n equal to this 2x of n minus x of n squared, then another square. And this is still memoryless because you see y of n only depends on x of n. So you know x of n, then y of n is totally determined for every n. Okay. So that's memoryless. And say this identity system is also memoryless. If y of t just equal to x of t, then obviously it doesn't only depend on x of t. And similarly, y of n equal to x of n. And there are a lot of systems with memory. Say this is something that's very intuitive. It's accumulator. So if y of n is whatever x of n from n to minus infinity to right now n, then it's like a storage system that you y of n just store every paste input. Then it seems like this is something with memory, right? Because you need to remember all the paste input. Okay. And similarly, in the continuous time, you can have an integrator that your y of t is the integral from minus infinity to the current time t, all the paste input. Then that's also something as memory because you need to remember everything from paste. Or you can have a delay signal. Y of n is just the x of n from the previous time step. Then that's also something with memory. And I guess something less intuitive if you have y of n equal to x of n plus 1. That's also something with memory, although it's looking into the future. But by definition, you need to be y of t need to depend exactly on x of t. So anything t less than 0 or greater than 0, it depends on then. Then that's something with memory. Okay? And then invertibility system. This is also quite, I guess, it is what it says here. So invertible means there's a system that can invert what your system did. So I guess more mathematically means that you have x of n goes through a system, become y of n, then there exists an inverse system such that you put y of n through the inverse system, you will get back to x of n. Okay. And okay, then from here, now from here on, we will, as in the homework, we will ask to prove whether a system, we will ask to identify whether a system is invertible or not, and we will ask to write a somewhat proof. Okay. So now, as you guys are not too, some of you are not too familiar with proof, so I just say this. When you prove this kind of thing, you want to be a legal rigorous, means that if you want to say it's invertible, then you need to find out the inverse system. And you want to say it's invertible. If you think it is invertible, then you need to find out the inverse system and do some calculation to show that whatever input your input is, and then you run through system and run through inverse system will get a back thing. And if you want to say it's non-invertible, then you need to get, I guess you need to get some input, and it says that that input will get some output, and that cannot be inverted. So I guess I'm skipping myself a little ahead, but I guess let's see an example of invertible first. So invertible system, say for example y of t equal to 2x of t. Then you can have inverse system being that the system, once again we use this funny notation. Now y of t is the input and we say that w of t is the output. We say w of t is 1/2 of y of t. Then you can see that you go through this, then w of t will have this 1/2 cancel these two. Then you get w of t equal to x of t. And similarly, so that's an easier invertible system, and we have a more complicated invertible system. So say your y of t is this accumulation system, so y of n equal to summation k from minus infinity to n, s of k. So we accumulate x from the negative infinity time to right now. Then you can also have an inverse system such that w of n equal to y of n minus n. Well, n minus 1, so kind of taking a difference. So taking a difference is actually an inverse of the accumulation, and we will get w of n equal to x of n. And so I guess for something non-invertible, then the proof you need to you basically need to show that two different input will give you the same output, then that's not invertible because because for the inverse system, one input can only give you one output. So here is an example that's not invertible. So y of t equal to x of t squared. So if you put x of t as input, so let's say, yeah. So whatever x of t as input and whatever minus x of t as input, you will get the same output, right? Because the square get rid of the negative sign. Yeah. Yeah. So yeah, so if you want to say your system is not invertible, you basically want to say you have two different inputs that give you the same output, then that's not invertible. Okay, so let's write something. Yeah. So x of t goes to y, then of t, then minus x of t will also go to y of t. So that's not invertible. Okay. Okay. Question. Okay. It's weird. Okay. Then the next one, causality. This is something that you kind of expect all the physical system has, but actually we will have a lot of non-causal system in the class. But anyway, causal means that, so this is weaker than memoryless. It means that the present output only depend on past or present input. Okay. But so what's important is that it doesn't depend on the future one. Okay. Okay, go back. So the future one doesn't affect your current response. Okay, this is very ugly. Okay. Anyway, yeah, the future input should not affect your present output. Okay. And if you want to write this in more mathematical form, that means that y of t is independent of x of t plus tau for whatever tau bigger than 0. Okay? And similarly for the discrete time case. Okay? And as we said, this is a very physical requirement that you think you should have on your physical system. So say you have the electric circuit here, this RC circuit, then you think, well, whatever voltage here only depends on the voltage in the past. It should not depend on things happening in the future. And similarly, if you drive a car, then whatever the speed of your car should only depend on how much force you put on your car in the past. It should not depend on your future of your car. Okay, so that's the very physical interpretation of being causal. And here we have a more example, more mathematical example here. So those are things that are causal. So once again, our integrator are causal because our y of t only depends on x of tau from tau less than t, because we are integrating from less than t. And also our difference, okay, so difference you would be careful. So the difference, so if your y of n being a difference of x of n minus x of n minus 1, then you are only dependent on x of n that's less than n. X on, very hard to say, x of something less than n, then that's causal. But then here we have something that looks very similar, but it's not causal. So if your y of n equal to x of n minus x of n plus 1, then this n plus 1 is bigger than n, so you are dependent on x of something bigger than n, then this is not causal. Okay? Or even easier, you have y of t equal to x of t plus 1, so you are looking into the future. So you are advancing your signal a little, then this is not causal. Okay. Or this is something else. So if you are averaging over x of n a little in the back, a little in the past and a little to the future, so this is some smoothing filter we'll talk about later. So this thing will look at x of n and go from past m step and future m step and averaging together. Then this thing is also not future. So you see that there are not causal system we also care about. Say you have like some computer programming processing your videos. Then because you are processing your video, you may look ahead of time and back of time. Then that's something not causal in terms of time step of your videos. Okay. And now we have something we can ask you to answer. Okay, so are those system causal? So I guess let's just do yes and no. So for those of you who think this is causal, raise your hand. No. And for those of you who think this is not causal, raise your hand. Someone? Okay, very small hand. Okay, so this is not causal. And y of n equal to x over minus n. This is not causal because, well, it actually depends on time. Okay, so because when n is less than 0, then minus n is bigger than 0. And in that case, the minus n will be bigger than n. So for example, when n equals to minus 4, then y of 4 equal to f of 4. So y of minus 4 depends on x of 4. But x of 4 is at a time step that's bigger than minus 4, right? So this is not causal because it's y of minus 4 depends on x of 4. So this is something we didn't quite say, but for this causal, we didn't quite say this, but when we say this y of t depends on x over t plus tau, etc. And also for memory rest, means that you need to satisfy this for all t. Okay, so I guess I should write it down. So this should be satisfied for all t. I should still say this for all t. And similarly, it needs to be for all n here, for all n. Okay. So if you just have one t that this is not satisfied, then it's not causal. Okay. Okay, go back. Okay, and yeah, now how about the second function? Sorry, second system. So y of t equal to x of t times cosine t plus 1. If you think this is causal, raise your hand. Okay, quite a few. If you think it is not causal, raise your hand. Some? Okay, I think we still get it correct on majority voting. Yeah, so this is actually causal even though you have this weird cosine t plus 1. So you see this is, the trick here is this is t plus 1. You think the t plus 1 is bigger than t, but it's not inside x. So this cosine t plus 1 doesn't depend on x over t at all. It's just something dependent on t. Okay, dependent on t, but it's still causal. And here is some explanation. So we have y of t equal to x over t cosine t plus 1. But this cosine t plus 1, as we say, you can think of it just whatever thing that depends on t, we can say is the g of t. Okay. So the g of t depends on time, but it didn't depend on x of t. Okay. And yeah, so that's a causal system. Okay. Yeah. So non-causal only means that you change the x of t and you change some future step of x of t, then y of t will change. But that's not the case here. Okay. So any question on causality? If not, then let's go to the next one. Okay, stability. So intuitively, stability, we have this picture. Although, yeah. So intuitively, the stability we want to describe whether a system is stable. So let's say we have a pendulum, then we think that if you are hanging your pendulum on top and your pendulum will go like back and forth here, then we think this thing is quite stable, right? You kick it a little bit and it will still just oscillating around here. And other way around, if you have a pendulum and let's say this is actually a stick, so it stays straight. But if you're a pendulum, then you have your weight on top of here, then you can only have a very unstable balance around here, and you kick it any bit, then this will just keep falling down, and the system is not stable because it will not stay around here and it will fall down. Okay. And okay, so that's the idea of stability. And we want to express this mathematically, and it's a bit funny. Oh, my file is different. Anyway, it should work. Yeah. Yeah. So that's the idea. Then we have a mathematical definition to try to describe this, although it doesn't quite fit what we want here. Yeah. Well, mathematical definition here is very, how should I say? Very large. Yeah. So anyway, the definition here is that we want a stable system to just not diverge on bounded input. Okay. So remember our input and output, and our system is stable if only if we have its bounded input and bounded output stable. I think you can have different definitions of stability, but this is what we will use in this class. Okay. Bounded input, bounded output. So that means that, so what's bounded input? So bounded input means that if your absolute value of your x of t is bounded, is less than infinity, so for every x of t you have some finite value, then for all t, then that's we call bounded. I guess this is a little weird, right? So this for all t also means this for all t doesn't mean for all finite t, and this for all t also means for this is kind of also for limit. It's easier if we see an example later. But anyway, yeah. So if a bounded input in this sense, and the output will also be bounded in the sense that all the y of t is less than 0 for all t. Less than infinity, I guess. This actually mean that, so if you want to, we'll see an example, but this thing, if you want to be clear, it means that exists some number b such that x of t is less than or equal to b for all t. Okay, that's a little more precise. Okay. Anyway, so if you are bounded in this sense, we have input bounded in this sense, then for a stable system, the output also need to be bounded in this sense. So there exists another number c such that y of t is less than rc for all t. Okay. And yeah, then the discrete time is similar, just turn t to n. Okay. So I guess let's see example. So y of n equal to a square of n. Then this is bounded input, bounded output stable, because if x of t is less than some b, then f of n is less than some b, then y of n is just less than your b squared. Okay. And what's something not stable is this bank account example we have before. So your y of n equal to the integer 1.01, y of n minus 1 plus x of n. So why is this not stable? Because let's say if your x of n is something very bounded, your x of n is 1. And then your y of n will keep accumulating, and you have this exponential growth part. right? Your x of n is bounded by 1, but your y of n will have this exponential growing. So it's, okay, so it's even easier. Let's say your x of n equal to u of n. Like for example, so you deposit like $1 in some place, x of n equal to u of n. Okay, x of n equal to u of n, not u of n, sorry, delta of n. Yeah, let's say your x of n equal to delta of n, so this is very bounded. This is less than 1 everywhere, less or equal to 1 everywhere. But then your y of n for n greater than or equal to 0 will have this exponential growth part. And that's not bounded by any number because it keeps exponential growing. So here we have some picture that give an idea of things being bounded and unbounded. Oh, what happened? Anyway, that still work. Yeah. So for unstable system means that you have this kind of bounded x of t, then your y of t will grow exponentially like in this case, and anyway will go to infinity at some place, maybe go to infinity at infinity. It's not bounded by some region. And if you want a stable system, then you have your x of t in some bounded area, then your y of t will also bounded in some area. Maybe it's oscillating very fast or whatever, but it's bounded in some region. Okay, so this is a mental picture of what's being unstable and this is what's being stable. Any question? Okay. So yeah, so now this is I think the most complicated property to check because so I guess you are still going to be asked whether to say whether something is stable or unstable. Then it's stable, then you need to prove that whatever you put a stable input, the output will. So whatever you put a bounded input, then you will get a bounded output. So we need to write some kind of proof that. And if you want to say it's unstable, then you need to find a counterexample. So you need to feed it with some bounded input and give some unbounded output to your through your system. Okay. And anyway, let's see through example. So those two things. And let's keep doing our thing. So vote by raise your hand. So are those BI/BO stable or not? So do you think this is BI/BO stable? Y of t equal to t times x of t. You think it is stable? Raise your hand. Okay. If you think it's unstable, raise your hand. Okay. Yeah, this is unstable. And what about okay? Let's see the answer here first. Okay. So why is this unstable? So it's because this is small t here. Okay. Even though it looks like just a small t, it's actually unstable. And as we say, if it's unstable, we want to give a counterexample. So the counterexample is very easy. Let's say your x of t equal to 1. Yeah. And this is bounded in our definition because x of t is less than or equal to 1 everywhere. Okay. And but if x of t is bounded equal to 1, then your y of t equal to t. And t is actually unbounded. It's not bounded by any value because as t goes to infinity, this goes to infinity. Okay. So yeah. So this notation is a bit funny. You think that y of t. Okay. So this is a little digression, but you see the definition is a bit funny because you see y of t here, y of t equal to t. Then it's not really infinity until t goes to infinity, but this means unbounded in our sense. Means that you cannot bound y of t by some number. So you cannot find some number a such that y of t is less than or equal to a for every t. Okay? Okay, so this is actually unbounded. And what about this? Y of t equal to exponential x of t. So I think it's stable. Raise your hand. Okay, a few. you think it's unstable, raise your hand. Even smaller number. And anyway, so this is actually stable, even though you see this exponential thing. But by our definition, let's say, okay, our x of t is bounded, so it's less than some b, okay? And so its absolute value is less than some b, then we know its value is between the minus b and b. And for t, then what's y of t? Y of t is exponential x of t. So we actually know the but exponential is like a monotone function, so we can just put those bounds into an exponential, and we see that the absolute value of y of t is actually between this exponential of b and exponential of minus b. And okay, so exponential of b can be very large, but it's a finite number. Okay. So your absolute value of y of t is actually bounded by this exponential of b, and so this is a bounded output, and so this is actually a stable system. Okay, y of t equal to e to the x of t, because you can give an upper bound on y of t for every t. Okay, any question? It is the most confusing property here, and it will get more confusing in the future when we talk about how to analyze the system in different way. But anyway, for now, you need to check this bounded input, bounded output. Okay, then we talk about the next property, time invariance. So this is actually a very important property. We are going to see it the whole semester. Together with the linear property we are going to see next. But anyway, what do we mean by time invariance? So the physical intuition on this property is that it's some system that just stay the same throughout time. Okay, so let's say this VRC system. I think if every component here is not breaking down, then through some amount of time, the system should stay at like very similar behavior, right? So your R and C is a constant of time. Then whatever your response to this V should be the same. Should be quite the same throughout different time. And similarly for your car, for like a suitable time frame, like if your car is not breaking down, then you are using your car today or using your car tomorrow should be roughly the same. And so the force and the velocity relationship should be about the same through different time. Okay. So that's the idea of time invariance. We think if our system, we want to use this property to describe systems that don't change throughout time. And okay, but that's a little tricky to describe, right? Because it's time invariance, but it can still have memory. So like I said, this velocity thing, you are using a car today, tomorrow is the same, but the velocity right now can depend on the velocity, the force like 2 or 3 seconds ago. Okay. So how do we actually characterize this? Is through this a bit funny relationship. Okay. So once again, x is input and y is output, and we say our system is time invariant if okay. So this is if whenever you have x, y input output pair, then you time shift to your x to x of t minus t0, then the corresponding output will be also time shift by the same time. So you time shift, so if you have x of t to y of t, then x of t minus t t0 will be shifted to y of t minus t0. And once again, this should be true for all t and t0, okay, and also for all xy pair. So whatever x of t given y of t, then x you should arbitrary times t0 will have the response of y should by the same time 0. Okay, so this is being time invariant. So I think this intuitively satisfies this, right? So those things can have memory, but if you shift the whole response from time infinity to time plus infinity, just shift it by some time 0, then the response just shift by the corresponding time. That means your system is time invariant. Okay with the definition. Now, now we see the example. This example I just give you answer. Okay, so y of t equal to sine x of t, and this is a time invariant system. And checking whether the system is time invariant, now you need to check through these things, and it's quite a bit of things to write down. So let's see this example how this work out. So we have arbitrary x of t as input, and the corresponding output y of t. Let's call this x1 because there is going to be a x2 that's a time shift version. Okay, so x1 of t, and they correspond to output y1 of t, and we can calculate y1 of t just through this relationship. System is given here. So y1 of t equal to sine of x1 of t. Just you go through this. And now we time shift our input. So we have another input x2 of t is a time shift of x1 of t. Okay. So y2 of t is a time shift of x1 of t. So x1 of t minus t0. Now we need to check two direction give you the same thing. Okay. So we can put this x2 of t through this system and get another y2 of t. Just yeah. So okay. So we need to check. Basically, we need to check the two kind of. I think these are the rectangular. Okay. So we kind of have. So we have like x1 and go through system give you this thing, and x2 and x1 we can also have another arrow. This is a time shift. Let's not say time shift. Let's just say t0. Okay. We basically want to check the two arrow commute. Okay. Okay. So x1 goes through system and give you y1. Then x1 give you time shift t0, give you x2. And we can have x2 doing time shift. Sorry, x2 goes through the system. Then, right? x2 goes through the system, give you y2, then it's the sine of x2. Then look at this, sine x1 t minus t0. And what we want to check is the same as this y1 doing time shift t0. Okay, and yeah, so if you put this thing through time shift, then it's the sine of x1 of t minus t0. Okay, and you see that it's actually same as this thing. So you have sine of x1 t minus t0. Okay. So if you go this way and you go this way, you get the same thing. Then it's then your system is time invariant. So let's write a bit better picture of what I'm thinking about. So you have x1 of t and you go through system. Then you get y1 of t. And you can also do time shift, then get x1 of t minus t0. And then there are two things you need to check. So you go through and you want to see whether this is the same thing. So you can either do y1 and the time shift, then you will get y1 of t minus t0. Or there is something, or you have x1 of t minus t0 goes through a system, and you want to see that's the same as this thing. And because we don't have a general expression for system, so that just is a question mark here. Okay. Okay, so this is kind of what we want to check. We want to see where this way and this way give you the same thing. And anyway, let's go back. So a little bit, and let's see another example. And this is something we can also do our small test. So is the following system time invariant? So y of n equal to n times x of n. If you think this is time invariant, raise your hand. If you think this is not time invariant, raise your hand. People are not responding. But anyway, this is not time invariant. Yeah, because you see the n here. Although I'm writing a very complicated function formula here, but you can just see this n here. So let's say it's very easy to see a counterexample of this being not time invariant. Let's say your x of n equal to delta of n, then y of n equal to 0. But your x of n, then you time shift it to. Okay, so let's write it down. Okay, so x of n, just because you have this n here, so where am I? Oh, so x of n equal to delta of n, then y of n equal to 0, and now you time shift this a little bit, so you have delta of n minus 1, then your y of n actually become 1 times delta of n minus 1, right? Because this thing only have a value at n equal to 1. And you see this is not time shift over 0. Okay. So this is time dependent. Okay. And what about the following system? y of t equal to x of 2t. And this is also not time invariant. And we see in this picture of the book here. So y of t equal to x of 2t means that you actually squeeze your signal. Let's say your signal is this square function. Then y of t will get squeezed by a factor of 2. So this is square from minus 2 to 2, then y of t will from minus 1 to 1. And you can kind of intuitively see this is not time invariant because this time equal to 0 is a very special place throughout this time axis. Because whenever you squeeze your signal, you are squeezing towards this t equal to 0. And you see why. So x1 of t squeezed to this 1 of t like this. But if you have some x2 of t, that's a time shift of x1 of t, shift by 2, so from 0 to 4. Then you run through this through system and you get y2 of t. Then it will squeeze towards 0, so it's something from 0 to 2. But if you just time shift your y1 of t, then you shift by 2, then you go from, then you will have a square from 1 to 3. Okay, so this 1 to 3 is different from this 0 to 2. And you can also check it through the algebra here. Okay, so this thing is not time invariant. Okay. And yeah, so it's also a bit annoying to check by algebra. And once again, if you want to say something is not time invariant, then you want to get a counterexample of two input that are time shift for each other, and their corresponding output are not time shift for each other, or like this example. So you have two input that are time shift to each other, and their output are not time shift of each other. I guess those two outputs are not time shift with the same time. Yeah. So in this example, the y2 here is actually a time shift of the y1, but the time shift amount is not correct, and that's also not time invariant. And so if you go through the calculation, you see that one of them will shift by, is y2 will time shift by minus t0, But if you want to be time invariant, it should be shaped by minus 2t0. So this is also another same. Okay. So everyone understand the time invariant property. And good, then we have about 4 minutes. Okay, we can do a little bit of linearity. So the last property of the chapter is linearity, and this is a property that exists in a whole bunch of systems, and it's mostly nice because it's very easy to compute. Makes a lot of computation at least a lot easier. And we like to build our electronic systems through linear systems because we can calculate their properties. And anyway, linearity is kind of what you expect. So it means that it has two things. It means that you have two different inputs and you add them together. Then the output will be the corresponding output adding together. So let's go through this more carefully. So to define this linearity of a system, we need to have two different input-output pair. So once again, this is for all. So for whatever input-output pair, so you have a y1 mapped to x1 mapped to y1, and x2 mapped to y2. So whatever this x1, y1, x2, y2 pair, and if you put the input, if you use x1 plus x2 as your input, then you will have y1 plus y2 as your output. Okay? And as we need to be, if you want to be careful, we need to define this plus min, and this plus just means for whatever n, then this value is x1 of n plus x2 of n. So you have a new signal that at every point the signal strength is x1n plus x2n. Okay, and that's the first of linearity, and the second property of linearity is that a of x1, so you multiply your signal by whatever number a here, then the output signal is also a times the original output. Okay, so you scale your input by a constant, then your output will scale by the same constant. And this constant is any complex number. Okay. So your system satisfies those two properties is called linear. And it's actually a little important that this a is a complex number here, as we will see in an example very soon. Okay. Any question about the definition? Okay. And we write this in discrete just for whatever, but for continuous, then it is the same. You just change n to t. Okay. Anyway, so a property of linearity we can already see here. So by the second line, then you see that you put 0 as your input to your system. Then 0 equals to 0 times whatever input. And so that should map to 0 times your whatever output. So the output should also be 0. So if your system is 0, is linear, then 0 input should give you 0 output. Okay. But anyway, let's see. Oh, okay. And although we only have two lines here, but you can kind of cascade those two property into a very general form. If you have taken linear algebra, you have seen this. So we can if you have this linearity property, then you can decompose your signal into a basis, right? Linear combination of different signals. So let's say if your input signal is a linear combination of whatever basis you pick is xk of n. So your input x of n is summation k ak, so some coefficient times some basis xk of n. Then you will have corresponding output. So your output will be some k ak yk of n, where yk is the response to xk. So x of k of n to yk of n. And similarly, you have the continuous time will have this property. And we are a bit over time, sorry about this, and let's have a break. We'll continue at 4:30. We have this still
今天助教有来吗？
助教好像没有来，你们先把那个作业放在这里，我之后再给助教。我的 thinking 失败。还有，你们就放在那个桌上那里吧，我之后再给助教。
第二个作业能交电子档吗？
电子档应该可以。
我已经交了，没注意到能不能？
应该可以，就是你寄给助教，然后确认他有收到。
好，谢谢。
所以现在做的是一定要交钱，是可以用一个人上去。
一任上传应该也可以，你跟助教确认一下好了。但是我觉得应该是可以的，他好像还蛮熟的，对。这个有点乱。可以，怎样？
这功课不是上个礼拜给吗？
啊？
功课不是要上个礼拜给吗？
功课上个礼拜给。
功课
一对啊，上功课一这样。
为什么现在可以给？现在还可以给？
现在还给功课一应该已经不能给了吧？已经对，是怎样？有人还给功课一吗？那给功课2。是功课2吧？对啊，功课2。对啊，这是功课2。啊，我看错了。因为有些题目很像。
对，它很像，对，
因为那个。
大学。
我要怎么把这个streaming 有点奇怪。算了。版本打架。
From that, from the homework I submitted on e-learn, so not paper-based.
Yeah, e-learn should be fine.
Okay.
Yeah. Am I still streaming? 你过来了。你帮我确认一下，我现在 stream 还有没有问题？
我刚看这个。
因为我这个有点版本冲突，然后
OK。
主要是换投影片的时候我怕它挂掉，所以我现在把投影片关掉重开，你确认一下。确认一下。然后同学用议论上传应该都可以吗？
可以。
对 ，OK。
嗯
，OK。等一下要切 Chapter 2的，不知道会不会爆炸。我这边其实我这边也可以开就是。我看一下，是上直播吗？操，这是谁？如何会动吗？这样。底类应该是正常的吧？我换几页看看。Okay, let's go back to our linear system. Okay, and as we said, for linear system, because we have those two properties, so additivity means that when you add your input together, you should have the corresponding output adding together. And also scaling or homogeneity means that you multiply your input by a constant, then you should also multiply your output by a constant. And if you pair those two properties together, then you see that you can decompose your input to linear combination of some function you like. Then your output should be the corresponding output in the same linear combination, because your x1 so because let's see how this decomposes, because the output of a1 x1 should be a1 y1 by the homogeneity, because you multiply x1 by a1, then the output corresponding to this should be A1 times the corresponding output Y1. And similarly for the A2, X2, go to A2, Y2, etc. And then you have A1, X1 plus A2, Y2 should have the corresponding output being A1, Y1 plus A2, Y2, because this plus sign should carry over here to plus sign by this additivity. And then you add another one, you add A3, X3, then that should give you plus A3, Y3 here. And you keep going, then you'll see that all those things signed together should correspond to all those things signed together. Okay. The summation AK, XK should give you output being summation AK, YK with the same AK, and YK being the output of XK. Okay. And okay, so let's back to those questions. Is this system linear? So y of t equal to t times x of t. Okay. And well, we basically check the check the property. So we have two things to check: additivity and homogeneity. So additivity. So let's first have two input-output pair. So x1 of t go to t x1 of t, because y of t equal to t times x1 of t. And x2 of t go to t times x2 of t. Then we have, we actually check the two relationships in one equation here. It's easier. So let's say we have x3 of t equal to a times x1 of t plus b times x2 of t. Then the corresponding y3 of t should be t times this x3 of t, and as t times this whole thing, so t times those whole thing. Then you see the t, you can do distributed laws, and that's a t x1 of t, b t x2 of t, and this is y1 of t here, and the t x2 of t is y2 of t here. So you see this thing is a times y1 of t plus b times y2 of t, and this is what is required by the linearity. Okay. And so we skip a little bit, but you can easily see that if you have this a1x1 plus ax1 plus bx2 go to ay1 plus by2, then obviously this satisfies the divisibility. Satisfy the additivity, because you can put ab equal to 1, then you have x1 plus x2 go to y1 plus y2. And if you put ab equal to a and you put b equal to 0, then you have ax1 go to ay1. So checking this, already checking both of these properties. Okay. And anyway, so that's the checking you can do. And I have more yes/no question we can test ourselves. So is this system linear? Y of t equal to x of t squared. If you think it's linear, raise your hand. If you think it's not linear, raise your hand. Okay, quite a bit. Yeah, it's not linear as seems so, as it seems like, because this doesn't satisfy both of them. But let's say you just check homogeneity, and it's non-linear because you have a x of t here, then you go to a squared y of t, right? Because you are a also getting squared, a squared y of t. Then this a squared is not a, so this is not linear. Okay. Now the second one is harder. Is this linear? Y of n equal to the real part of x of n. If you think it's linear, raise your hand. If you think it's not linear, raise your hand. People are not raising your hand. Maybe you need a little time to consider. Okay, let's try again. If you think it's linear, raise your hand. If you think it's not linear, raise your hand. about the same. Okay, this is actually a tricky question. So I think it's very linear because this satisfies oh, okay, let's keep this. This satisfies addibility because, well, the real part you can add together. So you have RE of x1 plus x2 equal to REx1 plus REx2. REx2. And it kind of, but now is RE of A of x1 equal to A RE of x1. This is true if your A is real, but it's actually not true if your A is not real. Okay. So yeah, this is a tricky question. So if x real, if x, that's a beautiful. So if your x of t is real, but your A equal to I, right? No, we are not using I. We are actually using J in this course. So if A equal to J, then yeah, then RE of J times your real function becomes an imaginary function, and that becomes 0. Okay. So yeah, so your J times your x of n. Wait, what's going on? Wait, huh? Why is this not recording? Okay. Excuse me. J. What? Sorry, this is weird. J times x of y. J times x of t will go to 0, and this is not equal to J times RE of x of J times RE of a. That's x is real, so RE of x is already is x equal to Jx of t. Okay, yeah. So yeah, this is a little tricky, but this system is not linear because the A in our homogeneity is required to be, we are defining it to be any complex constant, and so you rotate this with some complex number, then it breaks the homogeneity. Okay. And in this example, you also see those two relationships doesn't imply each other. Okay. So we can have one true, another not true. Okay. Okay. And now another question. I guess we have an answer here. Is following system linear? It looks very linear. Y of n equal to 2x of n plus 3. It's a linear combination of things, but linear shift of x of n. But it's actually not linear because our definition is a bit funny. Yeah. And that's because homogeneity is a very strong requirement. Remember we said that if you are linear, then you put 0 as input, you should get 0 as output. And here is not the case. If you have a 0 as input, you get 3 as output, and that's just not correct. And that will break linearity as we've checked carefully. Okay. So I see that you put x1 go to some y1 and x2 go to some y2, and you have x3 equal to ax1 plus bx2. And then you do all the calculation, you see you have extra 3 times 3 times 1 minus a minus b here. And so if your a and b are not adding together to 0, then this is not 3. Okay. Actually, what do we want? We want, oh sorry, 1 is 0 here, right? Let's see. Okay, so a and b should add up to 1. But anyway, we have another easier counter example. So let's say your x1 equal to 0, then your y1 becomes 3, and x2 equal to 0, y2 becomes 3. Then you adding that together, then x1 plus x2 is still 0, but y1 plus y2 is 6, but that's not equal to 3 that you get by going through this system. Okay. 点点什么东西？什么？哦 ，OK， 哦 yeah， I mean this， oh yeah， oh yeah， so we have this x1 0 go to y1 3, x2 0 go to y2 3, then x3 0 will also go to y3 3, but 3 is not equal to 3 plus 3, so this is just 0 should go to 0 once again. And yeah, so this is not linear by our definition, but we think this looks very linear, so we give extra definition, and says that we can call this incrementally linear. But I don't think we actually use this definition much later, but it's something nice we can define something looks linear and call it linear. Anyway, incremental linear means that when you have an input-output pair and you take a difference, and the difference is linear. And so I guess basically it's a system that can express as a linear system plus some constant, not quite constant, some zero input response. So it's a linear system plus some function, another signal y0 of t, which will be your system response when your input is 0. So here the 0 response is plus 3 here, and you have a linear part, that's y of n equal to 2 times x of n. And we'll not see too much of this, so let's stop here. This is a definition of incrementally linear. And for the other part of the course, we will stay talking about linear system having this more restricted definition of linearity. You need to have both additivity and homogeneity. And homogeneity means that you have 0 input, then you have 0 output. So any question about this? So we went through a lot of property today. And anyway, so this is a summary of this chapter. If not, then we will talk about a lot more about this LTI system, that a system that is both linear and time invariant. Okay, so no question, and let's try to switch slide. Okay, now this is hard. Excuse me. Okay, let's see if we can get everything correct and not break OBS. And even breaking PowerPoint. Save to this, and okay. Let's see. So chapter 2 here, and OBS I'm still streaming. Am I actually still where? Is OBS able to see chapter 2? Here. Are we good? It's still switching, but it's still streaming? Okay, hopefully it's good here, and switching around. Anyway, this is chapter 2. We are going to talk about linear time invariant system. It's okay? Okay. yeah, as we say, we are going to talk about linear time invariant system. And this is basically what we will analyze throughout the whole semester, because it's very nice mathematical property, and it can, well, it's very restricted, so it has very nice mathematical property. But even though it's very restricted, it's able to do a lot of signal processing we want to do in our real life applications. So they are very nice, linear time invariant system, LTI system. And anyway, so quick reminder of what we just talked about an hour before. So what's linear and what's time invariant? So linear we just talked about, hopefully you still remember. Linear means that whenever you take two input-output pair, x1 to y1, x2 to y2, then any combination of this input alpha x1 plus beta x2 should have the output should be the corresponding linear combination. So the output should be alpha y1 plus beta y2. And the time invariant is something hopefully you haven't forgot, but it means that whenever you have one input-output pair, so x mapped to y, and you shift this x by arbitrary time shift, so x go to x of n minus n0, then this y will have the same time shift. So y will go to y of n minus n0. So we are going to see that we can characterize a system that satisfies both of those properties by a very nice way. And LTI system is just a shorthand for linear and time invariant system. Okay, let's see what we want to do with this. Okay, so first we'll start with all the analysis of LTI systems on discrete time, because it's a bit more intuitive and easier to analysis. And we start with more reminder. So remember we defined this unit impulse function. This delta function is a very simple function. It has delta of n equal to 1 and n equal to 0 and equal to 0 everywhere else. And why we want to do this is because we want to use linearity, right? We talked before that because of linearity we can decompose our input signal to some linear basis. And what's a better linear basis than like just x at every value? Okay. So first we can decompose our whatever input into the linear combination of impulses. Okay. So here is the example. So you have x of n. Then why don't we write it as x0 times delta of n? And we know we can also time shift this delta of n and run, right? And so we can have x of 0 times delta of n will representing the 0 part. And say for this minus 2, we can have x of minus 2 times delta of n plus 2. We shift this delta of n here, so delta of n minus plus 2. Then this x of minus 1, we can have this minus 1 spike here. We can write it as x of minus 1 times delta of n plus 1. And for the n bigger than 0, we can also have this x1, x2, etc. So we represent each spike by this x of n times delta of n minus k. Okay. And yeah, so we write x of n as a linear combination of a whole bunch of impulses. So x of n can be written, any x of n can be written as linear combination of impulses shifted by some time. Okay. So for this example here, we see this is x of minus 4 times delta of n plus 4, etc. So it can be written as this kind of summation, and if you make this even more formal, then you can write this summation with a big summation sign. So with summation through some k from minus infinity to plus infinity, x of k. So for example here we'll have k equal to minus 2, k equal to minus 1, k equal to 0, k equal to 1, k equal to 2, etc. So we have x of k, so the x value at the point you want to look at, and the corresponding shifted impulse, so delta of n minus k. So this can be expressed for any signal. You are writing your function x of n as a linear combination of your function at some value times impulse function. Any question on this decomposition? It's just thinking your function as a whole bunch of impulse at different time steps. Okay, so here we haven't done much. And so here we haven't do any system thing. This is just writing your signal as a linear combination of impulses. And now we look at our system. Okay, so we use our first property. Our system is linear. This is why we want to write your signal as a linear combination. Then if your system is linear, then then we have write our signal as a linear combination of signals. Then we know it's linear, then corresponding output should be also the linear combination of a corresponding output signal, but with the same coefficient. So the x of k here is like the ak before, so we should have x of k here. And but now we have a quadrant, so we need the corresponding outputs, right? So what are the output of the, so if the input is delta of n minus k, what's the output? For now, we just say, give it a name. So we just say it's a whatever function, we call it h sub k of n, okay? So h sub k of n is the output corresponding to delta of n minus k. And we have a small table that summarizes the correspondence here. So your input is x, then output is y, and the input is delta of n minus k, then output we just call it h sub k of n. It's like an arbitrary function. And later we'll also see that we'll call when k equals 0, then that should be h sub 0 of n, and that's spatial, and we'll call it h of n. Anyway, for now, let's see some example. So the x of n, that just has 3 spikes here. And the corresponding output, you will have like something quite arbitrary. So we will need h of minus 1. It might look like this, and h of 0 might look like this, and h of 1 look like this. So you want to calculate the output as the summation k is k h of k. Then you want to multiply your this quite arbitrary h of k with your x. Yeah. So okay, sorry. So here we see these 3 different impulses. Is x1 at x of minus 1 impulse, and x of 0 impulse, and x of plus 1 impulse. We will give the corresponding output response. This is so it's x value times the corresponding h value. Yeah. So x minus 1 times h minus 1, x0 times h0, then x1 times h1. Okay. And then you sum those 3 together, you get the output. Okay, so that's a way to view this linear system. Okay. Okay, so this is a system that's linear, but it's not quite time invariant, because we see if it's time invariant, then it's even easier than this. Okay. So here we have these 3 h that are quite arbitrary, but actually if your system is time invariant, they cannot be so arbitrary, because if a system is time invariant, then h of k should be h of 0 of n minus k, because you see delta of n minus k is a time shift of delta of n, right? So by the time invariance, this dot h sub k of n should be the time shift of this h0 of n. Okay. So if your system is time invariant, then you cannot have these three things look different. You will actually just have h of 0 here, and this h minus 1, h plus 1 will just be a time shift of your h0. Okay, because it's time invariant. Okay, so that's very nice. We only need to, because all the h of k is just a time shift of this h of 0, then we can just express this whole thing by h of 0. And because it's only one h, then we can just abbreviate it by h of n. Okay. So everything is just decided by this h of n. And you sub those two equations into this thing here. And as you see that your y of n equal to summation k from minus infinity to infinity x of k, h of n minus k. Okay. So this is very nice. You see that every linear time invariant system is just characterized by this h of n. Sorry, is just characterized by this h function. You can just calculate this, and then you will get your y of n. Okay. And some more thing. So this is called a convolution, because the right hand side here, this is summation over k, sk h of n minus k. You can think of this as an operation that act on a function xn and a function h of n, or in our notation should be a signal xn and a signal hn. It's a little weird. Let's call it function. So you have function xn, function hn. Then you can do the summation of k, and you get another function y of n out. Okay. And we'll do it in this notation. Although this is a bit funny notation because there's 1n here, but you have 2n here. But anyway, we'll write this summation as this notation x of n, then convolution by this dot symbol here of h of n. So when we write x of n star h of n, we mean this. We are doing the summation k from minus infinity to infinity x of k h of n minus k. And this is somewhat correct here. You see the k is a dummy variable here. So k is getting summed over. So this is a function of n. Okay. And so we're going to see soon something we need to emphasize a bit more. So don't confuse don't confuse n and the k. And yeah, so it's very confusing, but here n is the time and the variable of our function, and for now k is the dummy variable, but we will get more confusing later. But just remember n and the k are different variables. And usually k should be summed over, so k is something that should not be in your answer of the problem, because it's like a dummy variable that you just do in your calculation. Anyway, so for now, any question on the derivation here? How we get here? So let's review once again. First, we say our system is linear, so we decompose our signal into those impulses, and those impulses have responses, those h sub k, and then we use the time invariant property, saying that h of sub k is just the time shift of h of sub 0. Then we arrive this relationship saying the output is just this h of 0 time shift to different place, then multiply by your input strength at different time step, and summing that all together. Okay, and summary page here. So important concept: any LTI system can be expressed as a convolution operation. So like this. Yeah, whatever LTI system, you have output y of n equal to h of n convoluted with your h of n here. And your LTI system is just we also have it here. So your LTI system is just totally decided by this H of n. Okay. So whenever you have a LTI system, you can just write down this H of n, and it will say everything the system does. And you can calculate. So you get the input, then you can just calculate output by doing this convolution, which is doing this terrible summation. Okay. And some other notations. Remember this delta of n minus k go to h sub k, and because if it's time invariant, then that's h of n minus k. And as we say, delta of n will go to h sub 0, and that we just call h of n. And h, if we say it in English, is called the unit impulse response. Okay. Unit impulse response will just describe everything of your LTI system. Question? Okay, if there is no question, let's see examples. So first example, give you some visualization of what's happening. This follows what we described before. So we see this y of n as some mean over different impulse response. Let's say your h of n look like this. It's kind of like a block. So it's 0, 1, 2, and 1 response. Response with 1 on time step 0, 1, 2. Then you have y of n equal to is some k, sk h of n minus k. And well, our x of n only have 2 spikes, not 0. So x of n equal to 0.5 at 0 and equal to 2 at 1. Then we have the first step is 0.5 times our response to this 0.5 spike is 111. Then we get 0.5, 0.5, 0.5. And the second impulse, so we have this one impulse, we have this 2, is height is 2. Then we should have a response as 2, 2, 2, and also time shift by 1. So it's 2, 2, 2, and it's 1, 2, 3. And so you have the first response of this spike like this, and the second response here. Then you adding together, they will look like this. So 0.5, 2.5, 2.5, and 2. Okay. So this is summarizing overall the LTI view of convolution. And here we are plotting against this, and that's the HO time of our system. Okay. Okay, now go to a little confusing thing, but quite useful for doing calculation. So we're doing the same thing, but we are visualizing it in different way. So this is basically we want to calculate y of n at a specific n. So it's actually not very easy to see, let's say, you have xn here and hn here, like what's y of 2 here. Okay. And so the second way of visualizing this is we want to like fix an n and get a way to visualize what's y of n for specific n by plotting things against k. Okay, so now that's where things get confusing. But anyway, it is quite useful to have a different visualization. So we want to plot, so mathematically we have y of n equal to summation k, x of k, h of n minus k. And so we try to plot this h of k, h of n minus k as a function of k. So we say k is a dummy variable that sum over, but we can still plot it. Okay. So x of k will look like x of n because, well, you just change k to n. And now we are basically trying to see, we have this h of n minus k for different fixed n, and we plot it on k and what it look like. And so h of minus k, And so this is actually not quite good. So I think the way to look at this is, never mind, it's annoying. But anyway, so you think about this as a function of k, then you think it's h of minus k plus n. And so this is both the time reversal and the time shift. And anyway, the direction will be when n is bigger, then your signal will shift to the right, so shift to the plus k direction. This is just correct. And anyway, so remember our h of n look like this. So you can have h of k also look like this. So you have h of k, then you change it to k. So you will have time reversal. So this will have the -1 because you have a minus k here. Then when you plus n, then your signal, when you plot against k, will, as we say, your bigger n, then will shift to the right correspondingly. And so what do we want to do here? We want to do so this also k is fixed. Then we want to see this h of n minus k for different n. So you see for different n, this thing getting pulled to the right slowly. And your y of n can be calculated as you multiply your s of k with whatever your h of n minus k here. And so you multiply, say, this with this, and you get 0. So then you sum over OK, then that's get you 0. Okay. So let's see a less trivial example. So let's say when n equal to 0, then your h of n minus k look like this, because you don't have n, so this is just a time reversal of, well, not quite time reversal, the k reversal of your h. But anyway, so this is your h of minus k, so it was this 1, 1, 1 from 0 to 1, 0 to 2, and now it's 0 to minus 2. So your h of 0 minus k look like this. Then you can just multiply this signal with your s of k. And you see a lot of them are 0, so they only overlap on this 0.5 and 1 here. Excuse me. So yeah. So when you multiply them together, so you multiply the signal on every time step, you only get this 0.5 is a 0. And then when you sum over k, because anyway we are calculating something for n, so k should disappear after the answer. So k gets summed over. So you sum over this multiplied signal, then you get 0.5. Okay. And the other one, let's say you want to calculate y of 1. Then your s of k is still the same thing. And the h of 1 minus k, as we say, you have the 1 here. Then your signal should get pulled to the right by 1 time step. Then you multiply this with this, then you get a 0.5 here and a 2 here. And then you get, adding that together, you get 2.5. And similarly, for y equal to 2, so for n equal to 2, then you pull this one more step, and you multiplication is 0.5 and 2, then you get 2.5. And y equal to 3, then you pull even more, then you have a 2 here by 1 times 2, so the whole thing is 2. And you are even further away, then this s of k and this h of minus k has no overlap, then it's just 0. And anyway, we see that we get the same result. So the 0.5, 2.5, 2.5, 2, as we expected. But now at every point, if you have this view, you can have a little faster visualization. So let's say n equal to 2, then you can just draw this and see the overlap with x of k, then you multiply together, then sum over. Okay. But okay. So to not confuse yourself too much, remember in the first view we are plotting against n, and in the second view we are plotting against k. So that's the difference. Any questions so far? Okay. If not, then this is something we'll do a lot in your homework and your exam. And let's see the examples. And yeah, we would like this geometric series cut off somewhere because we have a closed form when summing over geometric series. But anyway, we have a lot of those examples and test questions, so get yourself familiar with. Let's see how this works out. If our x of n equal to alpha of n times u of n, and we assume alpha is something less than 1, so you have a decaying signal. And your h of n equal to u of n, so this is actually a very large response, it's an infinite response. But anyway, so the question is what's the convolution of them? And we can see, and yeah, so here we use the second view to get us some intuition. So we plot in this k view. Okay, so x of k, as we say, x of k will just look like x of n. So it's still this decaying thing cut off at t equals 0, because of a u of n that will cut off everything n less than 0. And we'll have h of k. So h of minus k will be time reversal. So instead of going to the plus infinite, we go to the negative infinite. Then we see what happens if we shift this around. So we pull this around with different n. So if n is less than 0, then this h of n minus k has no overlap with x of k. So that should just be 0. Then as we pull this h of n minus k to the right, you see it has more and more overlap with this x of k. And yeah, we'll get more and more thing. And what's the overlap actually being? It should be this alpha of k summing from 0 to n, right? Because your h of n minus k only go up to n. Okay. So yeah, your y, which is a convolution of x of k and h of n minus k, is summation of k from 0 to n alpha of k. And this thing you can you can just plug in formula and get it y minus alpha to n plus 1. Okay, and but this is a little tricky question because there is another term that's u of n here, because this thing is 0 when your n is less than 0. Okay, so yeah, be careful. You also, so those things are always separated in cases, so it's actually a bit annoying to deal with. But those are the questions we work on. So we see that this overlapping thing only happens when your n is greater or equal to 0, and when n is less than 0, it's just always 0. So the n always less than 0 case, we'll just write u of n here. So, or there are multiple ways to do this. So you can either write u of n here, or sometimes in your answer we just write this in cases. Okay, so you can also just write, let's say, where, okay. You can also just write y of n equal to 0 for n less than 0, and whatever thing here, and n greater or equal to 0. Okay, so this is also valid answer, but you need to be careful about the cases. And also you can do this a little more algebraic way. So you can also see that y of n equal to the summation k to minus infinity x of k h of n minus k. Then you remember your h of k look like this. So this u of k here, okay, let's go back to our pointer. This u of k here will cut your summation from k, the lower bound of your summation to k equals 0. Because every k less than 0, this is just 0. Then you also have h of n minus k. H of n minus k actually equal to, because our h is actually u, so this is u of n minus k. So this is this u of n minus k is 1 only when n greater or equal to k. And the other way to see this means that k is less or equal to n. So that means that this upper bound should be cut to n. So you can also algebraically see that from this u of k here and this u of n minus k here, you have upper bound and lower bound cut to 0 to n. Okay. But yeah, but you see then, you want this formula is only happen when n is greater or equal to 0, right? Otherwise, the summing from 0 to something less than 0 doesn't make sense. So you need to handle the cases carefully. And we were 3 minutes, and can we finish this? So I guess maybe. So we have a very complicated example here. So here, once again, want to do convolution, but we have a lot of boundary now. So our x of n, actually we kind of will switch a role, but it doesn't quite matter. So x of n now look at this block. So it's 1 from 0 to 4, and our h of n now have this exponential thing, alpha to n. But I guess doesn't matter. But we are plotting here for alpha greater than 0. So let's say alpha n look like this. But they also cut off it from 0 to 6. So h of n only have value from 0 to 6. Yeah. And I want to find out the convolution. And so skip this for now. So let's see how this works in our view by plotting against k. So x of k once again will just look like x of n. So it's something from 0 to 4. Now our h of n minus k. So first we need to reverse this, do time reversal on this thing. So it should be some something like 0 to minus 6, and we'll pull it around for different n. And we'll see how the overlap goes when we have different n. So different n will pull this h of n minus k around this k axis. And we see that for n less than 0, this thing and this thing has no overlap. So it should just be 0. Okay. And now we have a second interval. So if n is between 0 and 4, then this x of k and h of n minus k has some overlap. And so the overlap is this thing. And if you calculate it carefully, it's once again a summation of geometric series. It should be from 0 to n over. Okay. So this height is. Sorry, I'm a little confused. Okay, so this height is 1. So it's 1 and alpha square, alpha cube, etc. to alpha to the 6. Okay. So if you sum over, then it's 1 plus alpha plus alpha, 1 plus alpha square. So it should be sum from 0 to n and alpha to the r. Anyway, so you do the calculation, then you see you have the summation of geometric series. Then you get this answer. And we keep putting this to the right. And the other interval, we have this overlap. And we are over time, and we just see very quick for now. And another interval where this boundary is between 0 and 4, and finally we have when this thing has no overlap with each other, then the y1 is 0. And yeah. So this is a kind of very delicate question we'll have in our homework and test, and we'll see more details next time. Okay. So any question? Or sorry for the overtime, or otherwise we'll have stop the class for now. Okay. Oh,忘开。所以，大家最应该作业做一做，回家一样的节奏。我你吗，同学？对。然后我想问一下，刚刚那个举的举的例子如果 x 有分丢多少分的话，然后丢多少分基本上都在 n 等于0的地方有分，那 y 有分就会是0，因为 n 等于0的时候在0。就是全部都。对。哦。这样我我还没讲呢，这样懂了吗？没有，还没讲的。对。没有，但是这样还没有是反例嘛？然后你要再把它 shift 一下，然后 shift 一下变丢它分减1的时候，那 y 有分会长什么样子？等一下。把它 shift 一下。我画图可能比较简单吧。这个可以画吗？可以。这样怎么拿？努力把它挖出来，这里有。这是要画图比较好笑，所以丢套分长这个样子嘛，就是只有在0个地方有一个1，这样对吧？对。然后对应到 y 有分就是全部都是0的东西，对吧？但是所以这个是0这样。然后，但是我把这东西 time shift， 然后变成0，然后1，这个是丢套分减1，这个这样的东西。那对应到 y 又是长什么样子 ？y 是 n 乘上我的 x 嘛，所以但是现在这条件是 n 1，所以不是1的地方全部都是0嘛，因为 x 是0，那 y 也是0。但是1的这一点的话，我会有这个1乘以 n 等于1，还是有一个1在这里。丢到分减1，然后这样子的话，这个 break 我们的 time invariant， 因为如果 time invariant 的话，那我这边 shift 往左边 shift 一个，不往右边 shift 一个，那这边这个对应的应该要是往右边 shift 一个，可是这两个都是全部都是0的。对啊，但是这两个就长不一样嘛，这个就不是全部都是0的东西。哦。对。OK。对。然后还有。就是然后他们为什么说这个为什么是？为什么对吗？我这样看要怎么证明，有点麻烦，虽然它是对的。我用个，因为这个东西不 symmetric， 所以有点奇怪，但是我们有一个没有讲的丢它方选的事情是，其实这个其实长得差不多的东西都可以变成丢它方选，就是如果你偷懒一点，其实你可以把它定义成丢它方选是，例如说一个三角形的东西，也不要三角形好了，其实丢它方选你直接把它放在中间，然后例如说这也是负丢它除以2，这也是正丢它除以2，然后这也是丢它的东西的话，然后这个东西再丢它，然后 后这个东西一样把 delta 变成0的时候，不对，我画反了，抱歉，这里是 delta 除以1这样。对，那这个的话就是左右对称了。
对，这样左右对称。
就是我要讲的是左右对称的事情嘛。
就是上面说这个是偶函数。
对，是偶函数。那这个是偶函数嘛？然后这个东西其他的极限也是delta方选，所以其实可以的。用这个看的话有点奇怪，因为你这个左右不对称。但是其实你可以定义成这个，然后它还是一样会变成一样delta方选。其实delta这个非常的随意啊，就是你这里稍微移一点啊，或者你把它变三角形啊之类的，都会有我们想要性质。所以我们只是想要它积分过去的时候答案是1，然后这个两边突出去的地方变成0这类事情。
然后那上次为什么就是为什么说就是乘上那个 unit impulse 的时候，就是乘上这个小小矩形会变成取那个就是上次讲那个它好像有个图，那个不用查。有一个对，就是这个到底什么意思？就是这个矩形，然后乘上就是怎么讲？就是我不太能想象什么叫一个矩形乘上一个
没有啊，这里乘就只是我应该有观点，乘就是把两个方选乘起来，就只是在每个 t 都把它乘起来。对啊。
然后就是说为什么是就是想象那个很细长的那个矩形，
很细长的矩形嘛，
就是要怎么乘上一个？
没有，就是一样，这个照定义的乘法。所以，例如说不怎么续长的这个矩形的话，例如说我用随便一个矩形的方选乘上一个这样的方选，那我乘完的话，这些东西就外面就全部都变成0了嘛。
对。
因为这是0。那乘这个的话，那就看这个高度是多少。例如说这个高度是10的话，那这下面就被乘10倍上来这样子，就是乘法而已。
对啊，再次，这是。
这就是乘法。例如说，好，我这里画多一点样子。我想想看要怎么画。我画手，要怎么画呢？比如这样子，然后例如说这个是2好了，那这个就会被放大2倍啊，它就会变成这样子上来这样子。
是哪一个是2？
那我说这个矩形的高度是2的话，如果是2的话，那你就会把这一个方选乘以2倍嘛，那就画在这边它变2倍。那如果是200的话，那就变200倍啊，就是这个意思。就是我在讲方选乘法，不知道这是不是你的问题？
等一下，为什么可以这样？
不知道，我只在定义那个，因为这就是这个方选定义啊。我有个 z of t 是 x of t 乘以 y of t。那如果 x of t 是2的话，如果 x of t 是100的话，那我 z of t 就是100乘以 y of t 啊，就是这样讲这种事情啊。你在问这个吗？我不太确定你想问什么。这个是这里的定义啊，这个我们写这样的话，就是说把这两个方选乘起来，那就是说主 t 把它乘起来，每个 t 都把它乘起来这样子。对啊。所以现在其中这个是个矩形嘛，那乘起来之后就会说这个矩形外面的东西都0嘛，因为就是它不在这个三角形距离的范围内，它都是0嘛。
对。
然后这里其实想要讲的事情只是说，这个三角形这个距离我们取得越来越小的时候，那我们就可以把我们就是它越来越小，但是因为我们外面都是0嘛，那这个东西基本上就只受，就是我们在看乘起来的这个东西跟 x of t 是什么关系嘛？
对。
那它就会受这个 x of t 在0到 delta 之间的间距之间的 x of t 影响。那我们说这个 delta 很小的话，那如果我们的 x of t 是个 smooth 的东西的话，有点微积分概念，就是 delta 很小的话，那我们就想说这个 x of 0到 x of delta 基本上都是同一个东西，那我们就说它是 x of 0就好了。 我们是在说 x over， 我们基本上是在说 x over 0大概等于 x over delta 这样子，因为 delta 很小。
哦，
对啊，就是在说这种事情
等一下在讲的是为什么它这个可以近似成这样？
然后就是因为我们有这个东西，首先这个好吧，我写字好了，想看要怎么写。这个 t 乘以 delta delta of t 等于delta x of t 跟0，然后这个是 t 在0跟不对，速度难查，反正我太聪明了。这个是 t 在0到 delta 之间，然后这是 r 的嘛，对吧？对，所以这里要说的只是 x of t 大概等于 x of 0，t 在0到 delta 之间，虽然 delta 勾出0，原是个很小的区间，就是好吧，我用多一点微积分好了，你知道微积分吗？对啊，我现在讲的就是微积分的事情嘛。泰勒展开始 ，x of t 不是等于 x of 0，再加上 t 乘以 dx dt，再加上 2分之 t 平方吧，乘以 d 平方 x dt 平方，就这样点的东西。Taylor expansion 记得吗？对啊，就好吧，你忘了那就。
那就是我只是想知道说为什么，就是
我不太清楚你的问题是什么。
就是就是这个东西要怎么乘起来？
什么意思？就乘起来啊？你是不会两个方选乘起来吗？我不懂你的问题是什么。
应该说就是这个图到底在干嘛？
就是在画这两个方选乘起来啊。你是不知道两个方选乘起来长什么样子吗？
应该是。
我问你问题好了，如果 x of t 等于 cos t，y of t 等于 sin t 的话，那 x t 乘以 sin y t 是等于什么东西？这个你知道吗？
这是 y of t，
对 ，y of t
就是 cos sin。
对啊，那这是一样的事情啊。你有一个 x of t， 然后有一个 delta of 三角形 of t， 那这两个方圈乘起来啊。你对于两个方圈乘起来有什么问题？我无法理解。
就是怎么讲？就是这个在 discrete time 的时候可以接受，但是突然到 continuous 的时候，我不知道为什么。
不是，那也是每个 t， 这合起来是一个方圈啊。就像你这里 cos t、sin t 是一个方圈嘛。那你这合起来不是一个方圈吗？你每丢一个 t 进去，就可以达到一个值啊，然后值是长这样子啊。你的这个东西我把它叫 z of t 好了，这样子你就比较高兴吗？
这个图到底在讲什么意思？
这个问题已经问过了。这个图就是在讲我这两个方选乘起来，然后不行，我觉得你要换一个问题问，我无法理解你在问什么问题。我想想看，你这样子没完没了。我要讲的是我在 visualize 这两个方选乘，首先你会乘两个方选吗？
对。
你会乘两个方选，那我觉得我要问你问题，你不能你这样子问。
好。
你知道这个图上 x of t 是谁吗？
这样什么意思？
这个图， 这个图上我们有 x of t，
对
吧？然后有 delta 三角形有 t， 所以我只把两个东西都画在这个图上。
对。
然后我要来这样子 visualize 说这两个东西都在图上，它乘起来会是怎样？然后呢，我知道 delta 三角形 of t 在这个外面的地方都是0。
对。
所以我们乘起来的时候，在这外面的地方都是0。
对，这可以。
对。然后在中间的地方会长什么样子？中间的地方呢，delta 三角形 of t 是个 constant， 是个这个三角形的高度。
delta 分之一的高度。
对，delta 分之一高度，抱歉，对，写错，delta 分之一的高度，对。然后 x of t 是 whatever 的东西，是 x of t 在这个区间的样子，对吧？
对。
然后乘起来的话，那它就会应该要是这个三角形分之一的高度乘以 x of t。
等一下。
你的方旋就乘起来啊？为什么这个要？好吧，你想一下。
因为它突然有个 delta 的宽度。
现在 delta 反正就是 fix 的东西吧，不管它，反正它就是有个 delta 的宽度。不知道我现在逐渐啊，你跟宽度有什么关系？跟宽度没有关系啊。我们不要管这 delta 好，我就是 x of t 就是 whatever 的东西，然后我有一个 y， 算了，不行，再讲你会更混乱。我想想看要怎么样那个。你有什么问题？
就是
你对于这个式子可以接受吗？
就是我们需要理
我也比较好。
这个小小的宽度。
还没有到那里，你先不要管。我现在只管我的长方形乘以 x of t 是什么意思，你知道吗？
就是两个函数值相乘而已。
对啊，两个函数值相乘。
对，这个可以啊。
OK。为什么会把你这个？没有。对，两个函数值相乘。然后我现在要讲的很小的事情是说，对不对？OK。所以现在要讲很小的事情就是说，如果这个距离很小的话，在这个很小的距离内 ，x of t 大概会等于 x of 0的事情，因为函数值我们可以想象说，你在一个很小的距离，你的函数大概就是这个 x of 0，然后乘以斜率这样子嘛，这是微积分啊，就是 x of t 大概会等于 x of 0加上 t 乘以 dx dt。希望你还记得微积分。
就是近似。
对，近似。
OK。
然后现在要做的事情呢，就是 t 很小，因为 t 是在0到delta之间的距离，所以我们就丢掉了。不对，回去。t 很小，因为 t 趋近于0。因为 t 被限制在这0到三角形的区间，然后三角形趋近于0，所以 t 也趋近于0，所以这样不见了，所以它就等于 x 等于0 ，x of 0。
这样。我应该可以接受。等一下，我想一下。